So, last class we are discussing about the linear quadratic regulator problem. Let us recall this problem. We have a dynamic system which is described by x dot is equal to a x plus b u, and x is the state vector whose dimension is n cross 1, u is the input vector whose dimension is m cross 1, and y is the output vector. So, our problem is to find a control law u of t such that this performance index, what we have described this one, the performance index is minimized. In other words, our problem is to find a control, our aim is to find a control law that will drive the state x t 0, t is equal to t 0, that will drive the state at t is equal to t 0 to a finite time t is equal to t f near the optimal near the origin or near the 0 state. So, for that one, what should be the choice of u, so that it will satisfy the performance index. Not only this one, it must satisfy our given dynamic equation 1 and 2, this one. This is our problem, and we have seen this problem, what we have considered the performance index. If you see this one performance, that interpretation of these weighting matrices, and the state weighting q is the state weighting matrix because it is associated with the state, r is the input weighting matrix, this is associated with that input, and we have a terminal cost, that means at time t is equal to 0, t is equal to t f at finite time, our state initial state will go to the near the origin, not exactly origin, but near to the origin, near to the origin at finite time t is equal to t f. So, this is the state terminal weighting matrix, this one, and if you do not consider that in the performance index that input term, that the control effort term, then if we minimize this one, we will see, or we can say that we do not have any control with the input effort. So, input effort may be extremely high, which we cannot directly apply to the systems. So, in other words, if you do not consider the state weighting matrix of that one quadratic performance index, this part, then we do not have any control on the state, this one. That is why we are taking the linear combination of state weighting matrix and input weighting matrix control effort. We are minimizing these two efforts, that means control efforts as well as the state weighting matrix effort, this one. So, this is our basic step, and the choice of q r, what q should be a positive semi definite and r should be a what is called positive definite matrix. And in our linear quadratic regulator problem, we have not considered that what we will derive it now, we have not considered there is no constraint on the u as well as x, that x and u are free, that no constraint imposed on x and u variables. Then when t is tends to infinity, instead of finite time, t tends to infinity, the state weighting matrix, that is x t f, will be assigned to a 0, because it has no physical significance of t is equal to t f, the function, that is state weighting matrix value is assigned to 0, because it has no physical interpretation there, because all the states will come to 0 asymptotically at t tends to infinity. So, this type of problem, when t f tends to infinity, this is called, this is infinity, this is called the infinite horizon problems, that also we will discuss later. So, let us see how we are going to derive the what is called LQR problem for finite time regulator problems. Regulator problems means our initial state are in equilibrium position. If there is a initial disturbance in the state is there, naturally this state will deviate from the equilibrium point, and it should come back to equilibrium point as quickly as possible with the application of control effort, that we have to find out that control effort, so that the performance index what we have considered, that is minimized. So, next is we are considering the solution of LQR problem, linear quadratic regulator problem for a finite time interval, problem finite time. That means, once again we define our aim is at driving the state x is t is equal to t 0 to a final state t is equal to t f, that means x t f, final state t f near about the origin or 0. Agree? That is our problem. For that one, what should be the choice of our control input, so that it satisfy our performance index, including the terminal cost, that performance index we have considered. So, let us call our problem is like this way: x dot is equal to, in general it is a x of t, u of t, and this, and x t 0 is equal to x of 0. Since we have described the system, our dynamic system is described into state space form, that is x dot is equal to a of t x t plus b of t u t, and x t of 0 is equal to 0. We have assumed that our system matrices A and B are function of time varying parameter matrices, and if it is time invariant, that A of t is constant, all the elements of the matrix A of t is constant, it does not change with time. So, our output equation, this is the state equation, and this is the output equation, and output equation C into x t plus, or you write is simply C of x t. Okay. So, this dimension x dimension n cross 1, that m u dimension number of inputs is m cross 1, and number of outputs you can p cross 1. Though in our regulator problem this output will not come into the picture, we are assuming that we will show you later, we are assuming all the state variable information x t are accessible to us or measurable to us, or in the sense the information of state variable is known to us. Okay. So, then our problem is to find a u such that it will satisfy this performing index. So, this is the terminal cost, which is f t x of t, this is the quadratic form in state, but at time t is equal to t f plus half t 0 to t f, then x of t q of t x of t plus, this is inside the bracket, plus u transpose of t r of t plus u of t bracket close d of t. So, I told you earlier that why half is taken into account, that in the performance index, that this half, when you find out the differentiation of Hamiltonian function with respect to u lambda or x, then you will see this half, and from there it will come 2 and this 2 and half will be cancelled. Otherwise, if you do not consider that 2 numerical value 2 will come through this expression. To avoid that one, we just multiplied by half. So, at what point the optimal value of the function will get it, that will not change, that as we have seen in static optimization problem, that if you multiply a performing index by constant or divided by a constant, that what is called optimal point at which the function will be optimal, that point does not change it. Okay, that is, we have seen it. So, this you can say as per our notation, this is the final, what is called terminal weighting matrix, and this is the state weighting matrix, which is greater than equal to 0, means positive definite. This is the control weighting matrix, that value is positive definite matrix, that we have discussed earlier. That must be from physical consideration also, that must be positive definite matrix. It cannot be positive semi definite, because when if it is a positive semi definite, control effort applied to the system will be 0. Then this is, that is why it is a positive definite matrix. So, let us form our, that is, if you just compare with this one, that is nothing but our SF, STF and x of t f function, and this whole thing is nothing but this half, you push it inside, then half x transpose q x u transpose r, this whole thing is nothing but a v, that integrand part is v. Okay. So, we can consider that whole thing, that whole from here to here, that part is v, which is a function of x t, u t and d t, including half, that is v, as per our usual notation. So, this part is the integrand part of that one. So, this whole thing I can write it T 0 to T f, that one, this whole thing, that is what whole thing will be replaced by that one only, you can say. So, let us see what is our Hamiltonian function. We know at this moment that how to generate or form the Hamiltonian function, form Hamiltonian function. You know h is a function of x t, u t, lambda t and t, and which is nothing but a our original system equation x dot is equal to a x plus b u. So, I will write it that our integrand part of this one, integrand part of the cost function, that is half, then your x transpose t q of t x t plus u transpose r of t u of t, that part, that means first is what integrand part of the performance index v of x, v of x is nothing but a b dot x function of what is called u and t is nothing but this, plus that in what is called Lagrange multiplier of this multiplied by our x of t x t plus b of u t, b function of t, this one. This is our Hamiltonian function, which is free from x dot, that we have discussed earlier, that one. Or if you see more carefully, it is nothing but our f of x t, u t and this, that whole thing is v of this. If you see, this is nothing but a v x of t, u of t and t, this one. Okay. So, where lambda with t is a co-state vector, co-state vector of dimension, that lambda is dimension n cross 1. Okay. So, this is the first step, you form that linear quadratic regulator problem means the system description, dynamic system description is given in state space form, and corresponding performance index is given, that terminal cost plus the integral of the quadratic form of in state and input matrix, that is input vector this. So, from this information I can find out the Hamiltonian matrix. Next step is step 2, necessary condition for optimality. So, what is the necessary condition? Del h del u of t is equal to 0. So, what is del h of del u? This is you see del h with respect to u. So, the u term is involved here and u term is involved here, and we know that if you have a x transpose p x, if you differentiate with respect to x vector, then result is twice p x. So, I will just apply that one, that u transpose r t u t, I am differentiating with respect to u t, that result will be twice r t u t. So, this twice and half will be cancelled. So, it will be half as it is, twice r of t u of t I am getting from this part. Again there is a function of u of t here. So, it is a lambda transpose b u of t, and we know that partial differentiation of a transpose x with respect to x, agree, that results is a. So, that I am applying here. If we apply is here, that one, then it will come plus b transpose t of lambda t is equal to 0, because this term you see this I can write it be it lambda transpose B u t, I can write lambda transpose B, I can write B transpose lambda whole transpose, and I made it into this form A transpose, then x means u this. So, this from there we are getting u of t, our control input is equal to minus R inverse, because R inverse B transpose of t lambda of t. Let us call our equation that Hamiltonian, this is equation number 1 you give it, this is equation number 1 and you give it, this is equation number 2. So, what in order to get this one, what we have used it, we have used these two things, differentiation of this with respect to quadratic function with respect to x of t. If you do this one, this result is twice p x of t. Another we did it A transpose x of t, this with respect to x of t is equal to A. So, these two things we have used in order to get equation number 2. So, once we get it this one, other two necessary conditions are this one. If you see the step 3, the state and co-state equation, state and co-state equation are given as x dot of t is nothing but a del h del lambda of t. That means, h is a scalar function, I am differentiating with respect to lambda vector. So, that see this one, the lambda is associated with this one only, the second part. So, if you differentiate this one with respect to lambda, so I can write it, this is nothing but a x plus b u. This if you are differentiating with respect to lambda, you see this I am differentiating with respect to lambda. So, this agree. So, I can write it, this is nothing but a whole transpose into lambda, that because this is a scalar quantity, this and this multiply is scalar quantity. So, I can write it A x plus b u whole transpose into lambda, agree. So, is same because it is a h is scalar quantity, this part is the scalar quantity. So, if you differentiate this with respect to lambda, I am getting this expression is A x a t x of t plus b t u of t. Okay, you have followed my point. This thing is a scalar quantity. What I will, I take the transpose of that one multiplied by lambda of t. So, this will be same as these values. Then I am differentiating with respect to lambda t, and that results is this one, that using that property, I mean that expression. So, I can write it now, next equation co-state equation lambda dot of t is equal to minus del h del x dot x of t, not dot x of t. So, now I am differentiating this with respect to x. So, x is involved here, x is involved here. So, from there I will set first one, I will get, if you differentiate with respect to x, you will get twice q of t x t, 2 cancel, q of x t I will get it. So, this will get it minus q of t x t, the first part. Then you see this one lambda transpose A x t. So, this I can write lambda transpose A x, I can write it A transpose lambda whole transpose, because this two I am writing A transpose lambda of t whole transpose is same as that part. So, I am differentiating with respect to x. So, it will be coming plus A transpose of t lambda of t. So, this, and let us call this is equation number 3 and this is equation number 4. Again. So, using equation number 2 means that one, this expression you use in equation number 3 and with 4, that means using equation number 2 u of t, replace u of t by this expression and then augment that equation with the co-state equation, and that will results that one. So, I am writing using 2 in equation 3 and with 4 using it 4 we have. So, x dot of t, that means if you write equation number 3, in equation number 3 you are using the expression of u of t, and then augment that u of t with then augment that equation 3, change equation 3 with 4. So, I am just doing this lambda dot of t is equal to this a of t, then b of u t, b is your b as it is, u of t is what, R inverse b transpose and lambda of t, and that I am writing x of t and this is lambda of t. So, the lambda of t multiplied by the a x, actually a x, a into x, b into u, b as it is, u I am writing minus R inverse b transpose lambda. So, this and this it is as it is, q of t, see this is I am writing q of t minus a transpose of t. So, this dimension is, since co-state vector and state vector dimension are same, each is n. So, this dimension n cross 1. So, now this is called is Hamiltonian matrix, and this whole thing is called Hamiltonian system, and this matrix dimension is 2n cross 2n. Now, look at this expression. Since our given system A t, B of t, Q of t, R of t is the designer choice. If you know the designer, whatever the designer has taken into consideration to design the LQR problem, then this whole matrix is known to us. That means, Hamiltonian matrix is known to us, and we can find out the its eigenvalues. Only difficulties is there, the parameter is changing with time. Agree? So, naturally the eigenvalues will change with time. Suppose if you consider A of t, B of t, R of t and Q of t is fixed, it does not change with time, then this is a constant matrix and eigenvalues we can find out, and this eigenvalues is a closed loop system eigenvalues. Agree? The way x dot is there, lambda dot of t is there, and we have a, in addition to this, there are n eigenvalues are there, which is closed loop eigenvalues, and another n eigenvalues are there, which is associated with the co-state vectors. So, let us see what is this represent, what is the eigenvalues of this one. What my main stress is here, without calculating anything, if you designer has selected R of t, Q of t and system matrix is known, I can find out what is the closed loop system matrix eigenvalues. So, this we can write it more compact or rather simple form, in the sense this I am replacing by another variables E of t plus minus Q of t minus A transpose of t, this equal to x of t dot lambda of t. So, let us call this is equation number 5. Again, now I want to show you here with a similarity transformation that these eigenvalues are nothing but a eigenvalues of closed loop system eigenvalues, and other values eigenvalues are eigenvalues of that lambda dot co-state vectors, eigenvalues of the system matrix of co-state vectors. So, use a transformation and this transformation I have used it I 0 I p of t, and p of t is a matrix whose dimension is n cross n. That means, this dimension is n, this dimension is n, this dimension is n, naturally all matrix dimension you know, and this is invertible. But look this one, this is invertible because diagonal matrix blocks are unity and it is a non-zero, that all columns are linearly independent columns are there. So, their inversion is exist. So, I am using that transformation, x is transformed to x bar and lambda is transformed to lambda bar of t, and that is equal to x of t and lambda of t. Agree. So, if you differentiate this thing both side, what we can write it? First is I this p of t, then lambda bar dot of t, lambda bar sorry x bar dot of t, this plus another term is differentiation of this block with respect to him 0, then 0, then 0, then p dot of t. So, this is that one. So, this into that your x bar of t and lambda bar of t, agree, is equal to x dot of t, right hand side x dot of t lambda dot of t. So, I know what is the lambda x bar dot of t, lambda bar dot of t. So, I will put it this expression in this side and then we will make some manipulation and simplification, we will get it. Now, this is the equation number, we have given up to equation number 5. So, let us call this is the equation number 6. Agree? So, from 6, so from 5 and using 6, from 5 and using 6, what you can get it? So, what I told you that in place of lambda x dot lambda dot, I will replace by this equation using 5 x dot lambda dot, I will use that one. So, right hand side equation is x dot lambda dot is replaced by a of t dot partition e of t minus q of t, sorry not transpose, or you can write transpose because it is symmetric matrix, minus A transpose of t. So, this equal to x of t lambda of t. This is the right hand side I have written, and left hand side will be as it is, as you have seen it, I 0 p of t I, then lambda bar dot of t lambda sorry x bar dot of t lambda bar dot of t plus 0 0 p dot of t and 0, this multiplied by x bar of t lambda bar of t, and this I have written. So, after simplification this thing you bring it that side, right hand side, this part you bring it that side, and x and lambda t you replace by transformation matrix, that is what we have, how they are related, x of t lambda of t related to with x bar of t lambda bar of t, that we know with this expression. If you recollect, this is the expression we have considered for transformation, this is the transformation. So, replace x of t lambda of t by this one in the right hand side of this part, and ultimately if you do it, that what we will get it, that one I just after simplification lambda dot x bar of t lambda bar dot, this is dot of t is equal to I 0 p of t I whole inverse, agree, whole inverse, then this multiplied by 0 0 p dot of t 0, then x bar of t lambda bar of t, agree. This is my procedure is my because this term I have taken right hand side, then this inverse I have taken both side I multiplied by inverse of that one. So, this is the then and this part will be what, say this will be inverse of that I 0 p of t I, this is I whole inverse, then a of t minus e of t minus q of t minus a transpose of t multiplied by this x and lambda t is replaced by x bar and this. So, if you replace by this one, this will get it your I 0 I p of t multiplied by x bar of t and lambda bar of t. Agree? This is the expression we got it, x bar of t, lambda bar of t. So, after just this and this you club together, and if you take this common, then this matrix multiplied by this matrix multiplied by this matrix, and resultant you will get a matrix of 2 by 2. Before that I have to know inversion of this one, I have to get it, because I know the inversion is exist, because this matrix has a n linearly twice n linearly independent vectors, because from this structure you can say twice n linearly independent vectors are there. So, this inversion is exist. So, now using what is called matrix inversion lemma, one can get these values are like this way. Matrix inversion lemma is what? I am just writing it here, matrix inversion lemma. So, if you have a matrix A, suppose we have a matrix A, B, C, D and they are partitioned like this way, agree, and it is assumed that A and D inverse is exist. We have partitioned in such a way that these are the square matrix and their inversion is exist. So, you have to find out this inversion of that one. So, that is the inversion, let us call it is P 1, that is P 2, let us put P 1 2, P 2 1. So, what I mean, we have a matrix A B, let us call A matrix, we have partitioned the matrix into 4 block in such a way that A matrix, this block and this block which will be a square matrix and inversion is exist. Then I can write P 1 is equal to A minus A, this one C sequence A minus then B D inverse C, P 2 is this corresponding D minus C, D minus C, then A inverse P, agree, A inverse n, then P 1 2 this one is equal to minus A inverse B, A inverse minus A inverse B, then P 2. When I have taken this P 1 2, you see P 1 2, I starts with A minus A inverse B, then P 2, this one P 2 already I have calculated, then P 2 1, tell me this one minus P 2 1 is this one minus P 2 1 I am finding out minus D inverse, then C, then P 1. So, this is the matrix inversion lemma. So, if you put the matrix inversion lemma here, agree, these places and simplify this one, ultimately I will get it final expression. I am writing x lambda bar dot of t, this what I will get it, I will just write it final expression. Please see the final expression. What final expression? This you use the matrix inversion lemma, then multiply this one, multiply this and this, these 3 matrices multiply, and then this and this you add it, then finally you will get it this matrix A of t minus B R inverse B transpose of T P of T. This is the first block, you will get it, and second block you will get it minus B transpose R inverse B transpose B inverse B of T R inverse B transpose B of T. Then this you will get it P dot of T minus A transpose T P of T plus P of T plus A of T. Please remember that P is a symmetric matrix. Here we have just considered this P is a symmetric matrix. The transformation what we have considered here, this P is a symmetric matrix. You can say P is equal to P transpose of T. So, this plus this is inside the bracket, this one plus P B R inverse of T B transpose of T into P of T plus Q of T. So, this is the 2-1 block, then the 2-2 block what we will get it minus 2-2 block I am writing minus A of T minus B of T R inverse of T into, this is continuation, B of T R inverse of T into B transpose of T P of T. Now, you see this block A11 block and A2 block. A2 block is same as A11 block preceded with a minus sign only, and other two A12 block, 1-2 block, 2-2 block is this one, that whole bracket multiplied by what, x bar of T lambda bar of T. Agree? Now, this is the equation. After transformation we got it this one. Now, I am telling you, this is the, you see, you select P of T in such a way, so that P dot of T minus of whole expression P A transpose P of T, P of T, A T, all these things will be 0. So, you find out the P of T value in such a way, so that this is assigned to a 0, it will be 0, or you can say I will assign this quantity is assigned to a 0. Agree? For that you find out what is the solution of P. That means, this quantity I will assign to a null matrix of dimension n cross 1. Agree? This whole thing I will assign. For that one you solve it P such that this equation is satisfied. So, if this is the so, I can write it that A of T minus B of T R inverse of T B transpose of T P of T, this is 0, and this is B of T R inverse of T B transpose of T, agree, this one, and this one is minus of A of T minus B of T cross, this is a cross multiplication R inverse of T B of T and P of T, Mind it, this is just same as that one, only preceded with minus. So, this whole thing I am writing this whole bracket after this, because I have assigned this is 0, assigned to this is 0. In other words, assign this one, find the solution of that what is called matrix equation, so that this expression will be satisfied. Find the solution of P for which this will be equal to 0. So, that whole thing multiplied by x bar of T, that lambda bar of T. Agree? Now, you see this is the block diagonal form, the eigenvalues of this one, this whole matrix eigenvalues is nothing but eigenvalues of this one and the block 2 to block eigenvalues. Whatever the eigenvalues of this block, the eigenvalues of this block will be same with opposite sign, because it is preceded with a minus sign, it will be opposite sign. So, this we can conclude this one, that eigenvalues of total state and co-state vector eigenvalues of this one is nothing but eigenvalues of this block and union of eigenvalues of this block, and these eigenvalues are same, only difference is the eigenvalues of this one with preceded with a minus sign, means opposite sign of that eigenvalues will be here. So, let us call this is equation number 7, this is the equation number 7. Now, we can see this one. So, we got it, what we made it a conclusion, that one, that if you have a co-state vector, if you do the transformation of this one, which we have seen, the augmented co-state and co-state vector can be represented into a upper block form. The eigenvalues of x star is nothing but eigenvalues of this one, eigenvalues of lambda dot is nothing but a lambda is nothing but a eigenvalues of that one with preceded with minus sign, that is why I have seen it. So, our general boundary condition, if you see boundary condition is given by H, I just we refer our the terminal cost, all these things boundary condition, T is equal to T f delta T f plus del S of del x t minus lambda of t, this is minus lambda of t, this is minus, agree, minus lambda of t dt, this whole transpose t is equal to T f and delta x f is equal to 0. Since our what is called T f is specified, since T f is specified, because we have considered our problem that our aim is driving the our initial state x of t 0 to a final state x of T f, t is equal to T f near to the origin. So, T f is specified. Therefore, delta T f is 0 and our x T f near to the original means x T f is not specified near to the original, and therefore, delta x f is arbitrary. So, then what is our boundary condition we are getting it here? Just see this one. So, this if you just put it here, x delta s of this differentiate with respect to x t, put t is equal to T f, agree, minus delta t is equal to T f, this equal to 0. So, therefore, we can write x T f is equal to, if you differentiate this one, if you see with x, or if you go back to this one, if you differentiate these things, that s term with respect to x and put t is equal to T f, this you are differentiating. So, what we will get it this one twice f x t and put t is equal to T f, then it will be a, it will come like this way. Therefore, lambda T f is equal to half twice f T f into x T f. So, this cancel. So, f T f into x T f. So, if you do the block diagram representation of this one, now we can find out our control law. Our control law, if you see, our control law is minus R inverse B transpose of lambda t. Solution of lambda t, if you know it lambda t, then I can find out the control law. Let us draw the our block diagram of this representation. Our reference input we have considered 0, because due to the initial condition what is this, we are showing it, this is b of t. So, this is our star and this is our integrator and this is x dot of t, the output is x of t, then this is coming is from here the state a of t, and this is a, if we just relate this one, x dot is equal to ax plus b, that must be u of t, then this is this, from there what is lambda, you see lambda expression, this is q of t, then this is coming to here, this is lambda dot of t, and you see the lambda dot of t, what we got it here, minus q x. If you see this one, lambda dot of t here, lambda dot of t minus q x x t. So, x t is coming, this sign is either you put it minus here or you put it minus here. So, this then A transpose lambda t. So, this is a integrator, and integrator output is your lambda of t. From there you are taking a signal A transpose minus A transpose of t, then it is coming here, or if you this, agree. So, that lambda of t now coming here, R inverse, this is the R inverse of t, agree. This is the R inverse, you see, because what is this u of t, just now we have calculated u of t by boundary condition, not boundary condition, necessary condition, u of t is equal to, just we got it, page number 3, that is u to t minus R inverse B transpose lambda of t. So, we have got lambda t R inverse B transpose. So, this is a minus sign, if you keep it here, agree, if you keep it minus sign here or here, it does not matter, agree, then this will be a u. So, that things are there. So, this is our controller part, if you see this is our controller part, and this part is our system, our given system. And what is this one? If you see this indicator, we have a initial condition x t 0 is equal to x of t 0, sorry, x of 0, this one. And we have a, just now we have seen, we know only what we know, only the our final co-state vector, final condition we know it, just now we have seen it. Just now we have seen it, this co-state here, this you see co-state vector, final condition we know it, that means we know lambda T f is equal to f T f x T f, because we know x T f where we want to keep the final state, agree, near the origin, near the our 0, that we near the origin we could. So, x T f is f T f, that one. So, now this this is corresponding to the co-state system, and this is corresponding to the state system, state equation. So, now see this one, how will you get the solution of these problems, because we have to solve, I told you that what we have to do it this now this. So, in order to solve this one, we have to solve that final condition. So, note the final condition on lambda t and together with final condition on lambda t f on t, final condition on lambda t together with x of t 0 and the Hamiltonian matrix Hamiltonian system. What is the Hamiltonian system? X dot of t and lambda dot of t, that expressions augmented system is the Hamiltonian system. Hamiltonian system of equation form, that means final condition on this together with x t 0 initial condition of the state and Hamiltonian system form the 2 point boundary value problem. So, we have to now solve this equation knowing the lambda t and final condition on T f, agree, and together with the initial condition x t 0 and Hamiltonian system, and Hamiltonian system is what? X dot of this lambda dot of t from this augmented system, what is the expression we got it with this, we have to solve this. So, it is called 2-point boundary value problems. So, now look carefully, see this one. So, how will you solve that one? How you can solve that one, that x t of that things, because x lambda t f, if the final condition of this one is known to you, that lambda t f, then we can solve this one in backward integration form. Agree? Now, see this one, lambda t f, t is equal to t f, final condition t is equal to t f, that if you know the lambda t f value, then I can find out lambda t f minus the what is called previous state of that one, that what is called, if the step size is capital T, T f minus t I can find out by solution of differential equation in backward process. And this whole thing is dependent on x 0, x t 0. If x t 0 is changed, then it is also changed, that solution of this one also change it. Now, how do you will solve this one? Next question is how you will solve these problems. That is our next problem. So, solution of this one is a, if you see carefully this one, this is a open loop solution, in the sense it dependent on the solution of this one dependent of x t 0, x t 0 means x 0 of that one. So, now how to form it, that remarks, you can write it remarks, the T p 2-point boundary value problem must be solved again if the initial condition change. If this initial condition is changed, we have to again you have to solve this one. Now, what is this one? How will you get it this one? X t f, let us call the x t f is known where we want to keep our final state. Agree? Because I told you at t is equal to t f, it is specified. That means, we are looking for a control law u that will drive the initial state as t is equal to t 0 to a final time at t is equal to t f, finite time at t is equal to t f, the state x is equal to t f will be near to the origin, okay, in final time in, that is our problem. So, now question is, this problem you have to solve in backward integration. If you know the x t f, backward you have to integrate and solve this one, and that solution depends on the x t 0. So, this is the if initial change. So, now we are looking for a closed form solution. Step 4, the closed loop optimal solution. So, how will you do this one? We know how lambda is related at time t is equal to T f, how lambda T f is related with x T f. So, assuming the structure of 8, we have what is the equation number? We have given equation number, let us call this is equation number 8, this is the equation number 8, agree? This is the equation number 8. Assuming the structure 8, lambda T f is equal to bracket, you can write it, that which one is x T f into x T f, agree, to relate the state and co-state, the state and co-state for all time, we have lambda t is equal to f of p of t into x of t. They are, because they are at t is equal to T f is f of T f T f. So, you are telling that for all the time t is equal to T f, it is related with this one. Then at t is equal to T f, what should be the P T f? Same as f T f. Again, at t is equal to T f, P T f is same as f T f. We know this relationship, we got it from the boundary condition of that one. Again, so that is the boundary condition, and that x T f will be near to the our origin mean equilibrium point. So, if you consider this equation number 9, then differentiating this one on both side, we will get p dot of t into x of t plus p of t x dot of t. Put the value of x dot of t in the expression, then you will get it, and lambda dot of t in that expression. What is lambda dot of t? It is nothing but a minus. What is lambda dot of t? We got it minus here. Lambda dot of t, you see lambda dot of t from equation 3 possibly, that you are going 4. Lambda dot of t is nothing but a q of t into x of t minus a of t lambda of t. So, I will put it, this values is there. So, it is q of t x t, q of t x t minus a transpose of t lambda t. Again, this equal to p dot of t x t plus p of t, and what is x dot? A of t x t, our system dynamic equation, b of t u of t. So, after simplifying this one, I can write it p of t, after simplifying, we can write p dot of t is equal to minus a transpose of t p of t plus p of t into a of t minus p of t b or inverse b transpose of p of t, this product p of t plus q of t is that one. This after simplifying we get, after simplifying we get that expression. Again, now you see the solution of this one is not dependent on the initial condition of that one. The solution of this one is not dependent on the initial condition, whereas when you have found out that this one lambda T f, this one, again when you will solve this equation in the backward integration, the solution of this u is dependent on the x of 0, this one. Okay. So, and this equation, this whole equation is known as matrix differential Riccati equation. In short, MDRE matrix, and it is a nonlinear differential equation, that our problem is solve this nonlinear equation, differential equation, agree. So, we must know our terminal conditions. We know PTF is equal to FTF, terminal condition is given. From there we have to get the solution. We will discuss the solution of what is called matrix differential equation in details next class. So, we will stop it here now.